As you watch this video, your brain is going to throw away as much information as possible while trying to preserve just a few key facts, I hope. The theory about how we trade off compressing an input signal while maintaining enough information for future tasks is explored by rate distortion theory or lossy compression. In the example shown below, you can imagine that you have some signal x drawn from a distribution, and then you add some noise and you get an output distribution z. So the key quantity that we're interested in for studying rate distortion is, first of all, how much information goes through this noisy channel. And that's really characterized by the mutual information between z and x, which can be decomposed in terms of differential entropy as the entropy of the output z minus the entropy of the noise, h of z given x. So the way that this is normally handled is with a bunch of assumptions. So for instance, we might assume that the noise is Gaussian, and then we can get an upper bound, but this upper bound is only tight if we assume that the input is also Gaussian, which is very unrealistic. We consider a different idea for constraining the mutual information in a noisy channel. The way we do that is by carefully choosing the noise distribution to have a very similar shape to the output distribution. So we say that the noise is sort of an echo of the output distribution. Because of the way mutual information decomposes in terms of entropy of the output and of the noise, these two distributions, because they only differ by a scale function s of x, it leads to a particularly simple expression for the mutual information between z and x that depends only on that scale function, the expected log determinant of that scale function. What's nice about this is that that scale function can be parameterized by any neural network, which gives us perfect control over the rate of this noisy channel. And it didn't require us to make any assumptions about the shape of the input distribution or the Gaussianity for the noise. You can do a lot of different things with this. So as a kind of classic rate distortion, we can look at omniglot, where we bound our rate at 30 nats, and we see how well we can reconstruct omniglot characters. So we compare echo with a VAE, where we add in this inverse autoregressive flow, which is a method to get around some of the Gaussianity assumptions in standard VAEs. If you scrutinize these, you'll see none of them is perfect, but that echo is doing a little bit better. And that can be quantified by looking at the average distortion in the two cases. Another cool application for compression is invariant representation learning. There's a paper that discusses the connection between these. And you can use invariant representation learning for things like compressing away bias between different measurement devices like fMRI scanners. So please have a look at our paper if you'd like to see how we derive this echo noise channel, and we talk about some of the applications for VAE and disentangling, for instance.